talked about heat being put into a system and had the equation of Q is equal to MC delta T. So we're going to take a look at the simplified case of I've got a block of aluminum, and we'll just make it 3 centimeters by 3 centimeters by 3 centimeters. And I put, let's say, 500 joules of energy into it. What will be the change in temperature? The review of some of this stuff. Or you tell me, what is Q?
The energy.
It is indeed an energy. What's
The change in energy of the system.
okay, almost there.
Heat energy.
Pardon?
Heat energy.
Or just heat? Okay, so it's heat, and what is heat?
Change in Connecticut.
We can be more general than that. What's the difference between, by throwing an object, putting kinetic energy that way, and heat?
The heat is the kinetic energy of the individual particles.
Okay. Let me spoil some of it for you. It's the transfer of energy because of a difference in temperature. So for right now, I've got hot water here and I've got a block in it which is absorbing. The kinetic energy is increasing in the block, which we would register as a greater temperature. Because there's a temperature difference between the block and the water. There's heat involved. So if I put 500 joules into this, that's 500 joules. And that is harmful. Is equal to the mass of this block. And what is the mass of the block?
Like I said, depends on the density.
And the density of aluminum is 2.7 grams per cubic centimeter, or 2,700 kilograms per cubic meter. All right, which is mass over volume. And that's something that potentially we'll see more of. Mass is just density times volume.
72.9 grams.
All right. Benjamin, you get the same thing?
Possibly.
Okay. I assume you did 27 times 2.7. All right, so because we're dealing with joules here, we'd probably prefer it in kilograms. And so how many kilograms is this?
0.072.
Kilograms times C. Now C is the specific heat. It is the amount of energy it takes in order to change the 1 kilogram or gram, whatever unit you're going to be using, kilogram probably, 1 kilogram of mass, 1 degree Celsius, usually. And specific heat of aluminum, I know I looked up and wrote down. Oh, there we go. Actually, I looked it up and I got several different values for it. There's 0.89 joules per gram degree Celsius, 0.9025 joules per gram degree Celsius, 0.908 joules per gram degree Celsius, and 0.903 joules per gram degrees Celsius. Those are 4 different values that seem to pop up. And it probably depends on how they get there, or the probably some other factors. My speculation is that the different factors depend upon the purity of the aluminum. That any aluminum that you would have access to, or that most people have access to, are not pure aluminum. So let's just use 0.9. 0.9 joules per, well, actually, if it's 0.9 joules per gram, then it'd be 900 joules per kilogram degrees Celsius times T. So what would be the change in temperature?
7.62 degrees Celsius.
All right. So if I took a block of aluminum and I heated it up to about 100 degrees Celsius, which is what I'm doing right there, and I put it in water that is room temperature, or ish, I would expect that the energy that the aluminum block will lose, because I'm putting it into a colder bit of water afterwards, I'm going to take it from there and put it into cooler water, the heat that the aluminum block loses should be the heat that water gains. If I have it in the right environment, I'm not going to lose any heat to the environment. In other words, if I use styrofoam, which is a pretty good insulator, thermal insulator, that the heat will stay within the confines of this. At least hopefully close enough to demonstrate some viability, veracity, some legitimacy for what we're talking about here. So, let's go through that scenario. I have a certain amount of water here. Assume perfect insulator. I really don't need dots that big. In other words, no heat is leaving the environment. Anything the aluminum loses, the water will gain. I have it initially at, we'll just say 20 degrees Celsius. I take my aluminum block, put it somewhere around 100 degrees Celsius. We'll get better actual figures when we do this. And so let's set up the equation. What's the basic principle we're dealing with here?
Conservation of energy.
Yeah. So the total change in energy is 0 because we've got a perfect insulator here. So that would be the change in energy of the aluminum plus the change in energy of the water is equal to 0. This is equal to the heat, because the energy is going to be exchanged because of the difference in temperature. So Q of the aluminum plus Q of the water. And apparently I changed my subscripts to H2O to W is equal to 0. Q of the aluminum is equal to the negative Q of the water. In other words, what one loses, the other gains. We have a formula over there, MC delta T. So I have mass of the aluminum times specific heat of aluminum times the change in temperature of the aluminum is equal to mass of the water, specific heat of the water, delta T of the water. Dramatic pause for questions.
Is there a negative?
Yes, thank you. It would eventually notice. And Michael, you didn't miss, I mean, what's on the board is,
Yeah, we're picking up where we left off.
issue. All right, let's expand this. I know changing temperature, well, changing anything is always what? How do you find change?
Initial.
Yep. So this is gonna be the final temperature minus the initial temperature of the aluminum. And this will be the final temperature minus the initial temperature of the water. I'm assuming the final temperatures will be the same. That one will heat up, the other one will cool down, and then eventually hit some sort of equilibrium. Distributing. And I wish I had given myself more room. Let's get rid of this. Anybody still need this part? So I have mass of the aluminum, specific heat of the aluminum, final temperature minus the initial temperature of the aluminum is equal to negative mass of the water, specific heat of the water. Oh, I'm just sort of rewriting what I had over there, not what I intended. Times the final temperature of the water minus mass of the aluminum, specific heat of the aluminum, initial temperature of the aluminum is equal to negative mass of water, specific heat of water, final temperature, plus mass of water, specific heat of water, initial temperature. I'm trying to find TF, so let's get this over on that side and this over on this side. And so I have TF is equal to mass of water, specific heat of water, initial temperature of water, plus mass of aluminum, specific heat of aluminum, temperature initial of the aluminum, divided by and then pause to see if there's any major error there. Oh, get a positive number, that's good. Well, let's plug and check. All right, so let's make up numbers here. So why don't we say this is 80 grams of aluminum and 120 grams of water. Where would you expect the answer to be? If you think of a specific heat, the larger the specific heat is, the harder it is to change the temperature. The more energy it takes. Now I do have more water than I have aluminum in terms of mass. Specific heat of aluminum, we have written here. That's C for aluminum. And specific heat of water is 4,186 joules per kilogram Kelvin, or degree Celsius, whichever one. So would you expect the final answer to be closer to that of water, or closer to that of the initial of water, or the initial of aluminum?
I'll do the water,
Why?
because it's both, it has more mass and it's harder to change the temperature.
Okay. All right, so I got 120, I guess we can do kilograms, 0.12 times 4186 times 20 plus 80 or 0.08 times 900 times 0.08 divided by 0.12 times 4186 plus 0.08 times 900.
.03 degrees Celsius.
All right. I assume you got the same thing? All right. So it should end up about 30 degrees. All right. Let's see how well this works out. I'm going to grab a triple beam balance. I don't suppose there's one in here. And let's see, triple beam balance. Oh, and I need graduated cylinder, water. Actually, I don't need the graduated cylinder, I just need water. I'm going to go ahead and pause this. All right, so we need to know initial temperature of the aluminum, initial temperature of the water, mass of the water, mass of the aluminum. We know C of the water, 8.1. That's not right, it's 4.186. 4186 joules per kilogram degrees Celsius, or Kelvin, whichever one. And C of the aluminum, about 900 joules per kilogram degrees Celsius. And that's all we need to know. All right, to get the amount of water, first find the mass of the styrofoam cup, then find the mass of the styrofoam cup with the water in it. All right, so 4.17. So mass of cup. I need to put enough water in there so the aluminum block will be covered. I feel like I have. $227 and 227.0 29. $227.29.
2.5, I think you said. Yeah.
All right, so what's the mass of the water?
We got 0.22312 kilograms.
All right. Now, if the block is sitting in the water long enough, and typically for a lab, as long as it's in there 2 minutes, you assume that the block is the same temperature as the water. Right now, it's 97.4 degrees Celsius, 6, 7, 8. It's going up and down. That seems to have stabilized. So the initial temperature of the block, 96.6 degrees Celsius. I would not expect it to actually be at 100 degrees Celsius because as the water gets to 100 degrees Celsius, it would boil off and taking energy with it. But I would expect it to be close. Well, that keeps creeping. I need the initial temperature of the water. Since the water's not been sitting out, I could not assume that it's room temperature.